Hello! Welcome to this lecture on solar heat gains. Solar heat gains are the third of the energy transfer processes we need to know something about to be able to make the energy balance and determine the energy needs for space heating and cooling. Solar radiation is captured by the facades and roofs of buildings. This increases their temperature. Solar radiation also penetrates into buildings through their transparent parts, the windows. The estimation of solar heat gains is not as straightforward as the estimation of transmission or ventilation losses. Maybe you remember the first law of thermodynamics and that we said that we would neglect the heat stored in the construction itself when making the energy balance. The solar heat accumulated in the construction can come from outdoors or from indoors, from the solar radiation passing through the windows. Let's first look at the outdoor part of the construction. Neglecting heat storage means that we will neglect the heat accumulated in outdoor walls and roofs. In reasonably well-insulated buildings or buildings with thick, massive walls, this is a reasonable assumption. In the first case, the solar heat will not pass the insulation barrier. In the second case, the heat will disperse all over the thick walls and we will have only a very limited effect on the indoor air. In non-insulated buildings with thin walls, however, this assumption is not valid and it would be better to account for these solar gains, although they generally still are much lower than the solar gains through windows. Anyway, in this course we will neglect the solar gains on the opaque envelope. So, we will consider only the solar gains through the windows. But how does solar radiation heat the indoor air? Well, as you may know, air is transparent to solar radiation, meaning that it cannot absorb it, and therefore air cannot become warmer from solar radiation, at least not directly. This is something you can experience easily when you're walking in the sun. If a cloud suddenly hides the sun, you feel much cooler, while the surrounding air has not had time to cool down. This is because it is not the air that is heated by the sun, but your body, which absorbs solar radiation. So, the same happens in a building. It is not the air that is heated by the sun, but the surfaces around the air, mainly partitioning walls, the indoor surface of outdoor walls and floors. Now, let's look at what happens with solar radiation inside the building. Here is a cross-section of our building. On the left, you see a window, and then going counterclockwise, the wall below the window, the floor, the back wall of the room, and finally the ceiling. Here is what happens when the sun shines on the window. First, a part of the solar radiation is blocked by the window. The window is not fully transparent to radiation and it absorbs a bit of it, which produces an increase of the temperature of the window. Second, the part of the radiation that is not blocked by the window arrives in the room and goes through the air, which I remind you is transparent, until it is absorbed by indoor walls and floors. By absorbing the radiation, they become warmer and warmer. At a certain moment, the walls and floors are warmer than the indoor air and start releasing their heat to the room by convection. Convection is heat transfer that happens by air movements along the wall, just like the alpha Y and alpha O convection coefficient you saw when studying transmission. This introduces a delay in the amount of heat coming free in the indoor air, meaning that steady-state static calculations, like we are doing with our energy balance, may not be accurate. However, for manual calculations aimed at rough estimates of the solar gains, we can consider the following two cases. For a light building, which is a building with little accumulative mass, for instance a timber frame construction, or still buildings with full glass facades, or buildings with an open floor plan and false ceilings, we can assume that all solar heat absorbed by the walls will be released to the indoor air within the same hour. This will be even more true if we would make daily or monthly analysis instead of hourly. For heavy buildings, which are buildings with a lot of accumulative mass, generally buildings with thicker walls using bricks or concrete, and where this concrete mass is not hidden behind false ceilings, we will assume that only 85% of the incoming solar heat will be released to the indoor air within the same hour. But what happens with the remaining 15%? We will just consider it as being lost. Of course, this is not true. This heat will come back later in the building, mostly at night when it becomes colder and there is less need for cooling. So we can neglect heat somehow. Up to now, we drew solar radiation by using a nice colorful sun. But the sun is not always shining. There may be clouds and the sky may be completely overcast. Does this mean that there is no solar radiation? Well, no, there is light. When the sun is shining, we call its radiation direct radiation. When it is not shining, we call it diffuse radiation. Generally, diffuse radiation is less than the direct radiation. When the sky is overcast, there is only diffuse radiation. When the sun is shining, both diffuse and direct radiation are present. When making estimates of the solar gains, we will always work with the global radiation, which is the sum of direct and diffuse. We sometimes also call it a total radiation. These radiations are generally measured by meteorological institutes. Unfortunately, they only measure the radiation on an horizontal surface or on a surface perpendicular to the sun, the so-called normal radiation. And what we need is the solar radiation on vertical planes, the windows, of diverse orientations. Going from the one to the other is a bit cumbersome, so in this course we will always use pre-calculated global radiation on vertical surfaces from orientations south to north. There is also always some solar radiation falling on the ground, close to the building and being reflected on the building, depending on the coefficient of reflection of the ground, which we call the albedo. We will neglect this radiation. When it is warm, it is important to protect the indoor from too much solar radiation in order to avoid too high temperatures or the use of too much cooling. There are many different types of solar shades and blinds. First, there are solar overhangs that block most direct radiation and only allow diffuse radiation to come into the building. Second, there are movable outdoor solar shades that block direct radiation too and to some extent diffuse radiation. The advantage of these shades is that you can choose when they are on or not. Here you can see a few examples. Third, there are many types of indoor solar shades, curtains, louvers or roller blinds, etc. As you can see here, the big disadvantage of indoor blinds is that they do not prevent solar radiation from penetrating inside the building. Radiation is blocked and absorbed by the blinds, the temperature of which increases a lot. And finally, quite quickly, the solar radiation is passed to the indoor air by convection. You can see in this table the solar factor of various types of blinds. We call it G-shade. The solar factor is the fraction of solar radiation passing the outdoor blinds by the solar radiation received by the window. If there are no solar shades, G-shade is 1. If the radiation is completely blocked, it is 0. You can see that external shades with a G factor of 0.2 are much more efficient in blocking the sun than the other types. At the beginning of this lecture, we saw that a part of solar radiation is absorbed into the glass of windows. There is also a part that is reflected back outdoors, and what remains is transmitted through the glass to the room and falls on the wall and floor. It is therefore very important to know how much radiation is transmitted through the glass. Well, this depends a lot on the type of window. Is it single glazing, double or triple glazing? Does it have a reflective coating or a low emissivity one? Is it colored glass? In the blue table, you can see typical values for the G factor of different types of glass. Here too, G glass, the solar factor, is the ratio between the radiation that comes into the room and the solar radiation received by the window. So, as you see in the table, single glass is the one resulting in the highest penetration of solar radiation with a G of 0.8. The more glass layers, the smaller the amount of solar radiation coming in. With triple glass, only half of the incoming radiation will pass the window. Gas filling and low emissivity coating are also useful, and reflective glass, often tinted, has the lowest solar factor. Only 20% of the radiation is passed into the room. Well, now that it has become clear how solar radiation works in a building, let's look at how to make estimates of it. First, I remind you we consider only the windows. If the solar radiation on a vertical plane of the same orientation as the window is P sol in watt per square meter, then the solar radiation hitting the window is the surface area of the window times P sol. So, to obtain the solar gains, we need to multiply this by the solar factors of the window and the solar factor of the blinds, if there are any, and also by the correction factor for building mass. For a light building, F will be 1, for a heavy one it will be 0.85. Don't forget that this is a very simplified method for manual calculations. And of course, if there are windows on different facades, you must calculate the solar gains through each window and sum them up to get the total solar gains inside the building. Be aware that P sol will be different for each orientation. In the northern hemisphere, for a window oriented to the north, P sol will be much lower than for a window oriented south. In the southern hemisphere, this will be the opposite. With this lecture, you have learned how to estimate solar gains by taking only the window into account. You also have learned that solar radiation is not absorbed by air, but by the walls and floors, and that the heavier the construction, the more heat is absorbed in it, and the less comes back into the air. We also have seen that the global solar radiation consists of direct and diffuse radiation and depends on the orientation. You also know now what the solar factor is and that only a part of the solar radiation is transmitted through the glass and through solar blinds. And finally, you are now able to make simple estimates of the solar gains. Thank you for your attention.